Hello everybody, this is the third section of the topic integer programming. The materials in this presentation corresponds to the material in the chapter 9 in your textbook, section 9.2. Okay, so let's take a look at the third example. A company can produce three types of clothing: shirts, shorts, and pants. However, it does not have the machine, so in any week that it wants to produce something, let's say shirt, it needs to rent the machine for $200 per week. If it wants to produce shorts, then it needs to rent the machine to produce shorts for $150 per week. And then to produce pants, it needs the machine that can be rented for $100 per week. And then to produce those types of clothing, it also requires labor and it also requires cloth. So the requirements for each type of clothing, for example, shirt requires 3 hours labor, and then 4 square yards of cloth is shown in this table. And then also, after the production, it can sell the product with these sales price. And then to produce each type of clothing, not only it needs to rent the machines that has been mentioned earlier, but it also has the variable cost that it has to pay for each unit of clothing. So that was the problem. Now we are asked to formulate that problem into an integer programming. As usual, I'll start by looking at the objective. It is said here that we are asked to maximize the company's weekly profit. So talking about profit, we must need to check what we gain minus what we pay for the cost. So here we gain money by selling shirts, shorts, and pants. So for example, each shirt that we sell, we obtain $12. And then we also need to check what kind of cost that we pay. So here there's variable cost. For each shirt that we produce, we need to pay $6. So up to this point, we can say that our weekly profit consists of what we gain from sales minus the costs that we pay to produce the products. But then in this problem, remember that the company does not have the machine. So it has to rent the machine whenever it wants to produce a certain type of clothing. So obviously we need to take those fixed costs into account. So anytime we want to produce a shirt, we need to pay $200. So we can say here that 200 times a variable saying that if we produce shirts, 150 times a variable saying that if we produce shorts, and then 100 times a variable saying that if we produce pants. So it's clear up to this point that x1, x2, x3 are related to the units of products that we want to produce, while y1, y2, and y3 are related to whether we rent a machine or not. Or in other words, whether we want to produce that type of product or not. Once we decide to produce, let's say, a shirt, even though just one unit, we will need to pay $200 to rent the machine. Okay, so after subtracting the selling price from the variable cost, we arrive at this objective function here. Now, based on the objective function, let's start defining the decision variables. So x1, x2, and x3 are the number of shirts or shorts or pants that we produce every week. Why is that the case? Well, because the selling price and the variable cost in the previous page are related to each unit of item that we produce. So it is obvious that x1, x2, and x3 needs to be defined as the units or the number of the items that we produce every week. As for y1, y2, and y3, as I said before, these are binary variables. It means that each of these variables is defined by either 1 or 0. So let's take a look at example of y1. So we're going to say that if we are producing any shirt, it means that we have to rent the machine. So y1 equals 1 if any shirts are manufactured. If we do not produce any shirt, it means we do not need to rent the machine. That's why y1 equals to 0. y1, y2, and y3 can only take either 0 or 1 because these variables represent either we rent the machine or not. Remember that whenever we produce an item, even if it's just 1 unit of that item, we need to rent the machine. Okay. Now let's move on to the constraints. How to identify constraints in an optimization problem? Well, without the constraint, you can just say, if you want to maximize the profit, you just produce an unlimited number of items. So you can sell a lot of items and then you get unlimited profit. But here you see in this problem, it is not possible to do that. Why? Because we have a limited number of hours of labor, and then we also have limited number of cloth, as shown in this table. So the first constraint says that we can only use at most 150 hours of labor per week. And then constraint 2 says that at most we can use 160 square yards of cloth every week. So clearly we are having these constraints that limit us from saying that we just produce unlimited number of clothing to get unlimited profits. Okay, so again, constraint is something that limits you from making unbounded decisions. Constraint 1 says that at most 150 hours of labor can be used each week. So start by writing down 150 in the right-hand side. And then because it says at most, so you put the sign less than or equal to. So whatever number of labor that you spent on the left-hand side must be less than or equal to 150. Now, how many hours do we spend? For each shirt, we spend 3 hours of labor. For each short, we spend 2 hours of labor. And then for each pant, we spend 6 hours of labor. So clearly it's 3 times x1, the number of shirts that we produce, 2 hours times x2, the number of shorts that we produce, 6 times x3, the number of pants that we produce. So the total number of hours that we spend here must be less than or equal to 150. The same idea is used to formulate the second constraint. At most 160 square yards of cloth, so you put 160 on the right-hand side. And then since it says at most, so you again put the sign less than or equal to. Whatever number of cloth that we spend on the left-hand side must be less than or equal to 160. Same as before, we see that for each shirt that we produce, we spend or we use 4 square yards of cloth. And then for each short, we use 3 square yards of cloth. For each pants, we use 4 square yards of cloth. So that's how we formulate these two constraints. So up to this point, after adding the sign restrictions, saying that x1, x2, and x3 needs to be greater than or equal to 0, they need to be integers, and then y1, y2, y3 needs to be either 0 or 1. This is our formulation so far. But take a look at this formulation. Do you think this formulation is correct? You may pause the video and take some time to think about whether this is a correct formulation. Let me give you the clue. It's about the y variables. Well, the answer is this formulation is not correct. Why? Well, let's see here that in the objective function, you have the y variables. But those variables, they do not appear in the constraints at all. What does this mean? It means that using this formulation, you may produce all clothing items without having to rent the machine. In this formulation, y variables have negative signs. So obviously, without involving them in the constraints, the optimization problem will be solved by setting these variables equal to 0. Okay, so y1, y2, and y3 will all be set to 0 because you don't have any constraint at this moment saying that if you produce an item, you need to rent the machine. Without the constraint, solving this optimization will always give you the solution of y1, y2, and y3 equals 0. So let's fix this problem in the next slide. So to make the formulation correct, we must ensure that y1 equals 1 if any unit of I is manufactured. In other words, once you're saying that you're producing shirts, even if it's just 1 unit, then y1, the machine for producing the shirt, must be rented. Or in other words, y1 must equal 1. And this is how to do it. We add these 3 constraints to ensure that whenever you produce something, you must rent the machine. To understand this constraint, let's see an example. Let's say you decide to produce 9 units of shirts. So x1 equals 9. So the first constraint says that 9 must be less than or equal to m1 times y1. So here, the m is a very big number. If you recall in your OR1 course, big M stands for a very big number, big positive number. Okay, so the first constraint says that 9 must be less than or equal to m1 times y1. So let's check the possibilities. If y1 equals 0, then that inequality becomes 9 less than or equals to 0. Okay, because if y1 is 0, anything times 0 becomes 0. So this inequality becomes 9 less than or equal to 0. We know this is incorrect, so it must not happen at all. So the only possible value of y1 that will happen in this case is y1 equals 1. Let's check the inequality. It will give us the result 9 less than or equals to m, which is okay, which is correct because m is a very big positive number. Okay, so by adding this constraint, you can see that whenever x1 is not 0, whenever x1 has the value positive, 1, 2, 3, 4, and so on, y1 is forced to take the value of 1. Take some time to really digest this constraint, that forcing y1 equals to 1 whenever x1 is positive. Now you might ask, what happens if x1 equals 0? Well, let's check the same constraint. If x1 equals 0, the inequality becomes 0 less than or equal to m1 times y1. If y1 equals 0, the inequality still holds. 0 less than or equals to 0, it's correct. If y1 is 1, it's also correct. 0 is less than or equals to m. So in this case, if you don't produce any shirts, Actually, you may or may not rent the machine. But of course, it doesn't make sense to rent the machine and pay the fee if you don't want to use it to produce any shirt. And also in the optimization problem, this will be taken care of because Y1 has the negative sign on it. So automatically, if you don't produce any shirt, Y1 will be set to become 0 in the optimal solution. Again, it is because it is more logical. If you don't produce any shirt, then you don't rent the machine either. Suppose you're going to solve the optimization problem using a software or something. Obviously, you cannot type M into the software. You need to put a big enough number. But how big is big enough? Well, let's see here we have in this problem, labor availability is 150 hours and the cloth availability is 160 square yards. So to determine M1, how many shirts at most that we can make, we just try to see that if we use all the labor hours to produce shirts, then we can obtain 50 shirts. Again, if we use all the cloth availability, 160 square yards, only to produce shirts, then we have at most 40 shirts. By comparing, if we use all labors, we can use 50. If we use all clothes, we can only make 40. So obviously, at most, if we use all resources, both labor and clothes, we can only make 40 shirts. So here, M1 can be set as 40. Because even if we use all the resources, both labor and clothes, we can at most create 40 shirts. So now your task is to verify that M2 equals 53 and M3 equals 25 using the same idea. So finally, we have the correct and complete formulation of the problem, the objective function, the constraints, including the constraint that say if we produce an item, then we must rent the machine. That's the main takeaway of this problem. You need to make sure that you understand this, and then you also can formulate these types of constraints. Finally, as always, don't forget to put the sign restrictions that restricts the value of the variables. As you can see in the syllabus, we're skipping example 4, so now we're at example 5. The problem is called set covering problem. So in this problem, there are 6 cities in a county, and the county wants to determine how many fire stations it needs to build. It would like to build as few fire stations as possible. But then for the safety of the people, it must ensure that at least there is one fire station within 15 minutes of driving time of each city. So for example, if you build a fire station at City 1, that fire station is effective to reach City 1 itself, and then it can also be used to reach City 2, because City 2 is 10 minutes away driving from City 1. How many minutes it takes to drive from one city to another is shown on the table. So as usual, I will start with the objective function. Here in this problem, we can see that the county wants to build the minimum number of fire stations. So it's kind of obvious that the objective function is the sum of the fire stations that we built. And since that we can only build one fire station in one city, so each variable here represents whether we built a fire station in that city or not. So the objective function is the sum of x1, x2, x3 up to x6 because there are 6 cities. And we may define, for example, x1 equals 1 if we build fire station in city 1 and 0 otherwise. So again, this is 0-1 integer programming in which the decision is whether you build in that city or not. Now let's formulate the constraints. It is said in the problem that at least there must be one fire station built within 15 minutes of each city. So it means that we have to set the constraint for each city. So for each city, we have to make sure that at least there's one fire station built within 15 minutes of driving to that city. So let's start with city 1. Suppose we're at city 1, we must ensure that at least there is one fire station built in either city 1 or city 2. Why? Because to cover the safety of city 1, it needs one fire station in a city that is either in that city itself or another city within 15 minutes of driving. In the case of city 1, if there's a fire station at city 1, it's good. If there's a fire station at city 2, it's also good because it may cover the people in city 1. So to formulate this type of constraint, we say that the sum of x1 plus x2 must be greater than or equals to 1. Let's see the next city, city 2. So for the safety of the people in the city 2, it needs a fire station that is built in either city 2 itself, or city 1, or city 6. Again, if either in city 1, 2, or 6 there is one fire station, then it is enough for the safety of people in the city 2. Because city 1 and city 6 are just 10 minutes driving from city 2, so it can cover city 2. If the fire station is in city 2 itself, of course, obviously it can cover city 2. So we go on by checking for each city, what are the possible cities that may reach that city within 15 minutes. So for city 3, city 4 can reach city 3 within 15 minutes. For city 4, we have 3, 4, and 5. For city 5, we have 4, 5, and 6. And then for city 6, we have 2, 5, and 6. And then as for the sign restrictions, we say that each variable needs to be either 0 or 1. Again, it means that either we build a fire station in that city or not. So this is the complete formulation of the problem. And this problem is called set covering problem because there are two sets involved in this problem. First is the set of cities that we need to cover, and then the second is the set of fire stations that we use to cover the cities. What we want here is that we want to have as few as possible elements in the fire station set to cover all the cities that we have. As usual, if you have any questions, feel free to leave your questions in the comments or just shoot me an email. Thank you.